Alright, so to start off our Unit 6, we're going to start to talk about an antiderivative. So we've been doing derivatives all year. This time, an antiderivative is where we actually think about working backwards. So instead of taking the derivative of a function, we're actually going to try to figure out what we had before that function. In any case, if you were to take the derivative of something, it would give you the equation that you know. So we're going to try to figure out the previous function that we had, okay, this antiderivative or working backwards idea. So the first type of shortcut that we're going to talk about for these antiderivatives is if we have a polynomial type function where that's like x to a power. Okay, maybe we'll say it's 3x to a power. So if someone asked you how to find the derivative of this, I think we'd be able to kind of explain it to them. We would probably say something like take the coefficient times the power. Okay, so it would take 3 times the power, and we know that would be our new coefficient. And after we do that, we have to subtract 1 from the power. Okay, so we'll bring down the p, multiply it by 3, and our new power would be p minus 1. Okay, we've been doing that for quite some time. That was the very first derivative shortcut we actually talked about. So now we're going to try to work backwards to help us figure out an antiderivative. So we got to try to figure out what was the previous function we had that would give us 3x to the p as a answer, okay, if we were to take the derivative of it. So what we're going to do is we're going to take these steps that we normally do for a polynomial function, and if we want to work backwards, we're going to do the reverse order using the inverse operations, okay, or the reverse operations. So instead of ending by subtracting 1 with the power, we're actually going to start our antiderivative calculation or process with this step, and instead of subtracting 1 from the power, if we do the reverse operation, we'd have to add 1 to the power. Alright, and then we're going to take the coefficient, and instead of timesing it by the power, we'd have to divide it by the power. Take coefficient divided by power. Okay, so this is going to give us a really easy and kind of quick method or shortcut to help us work backwards, aka find an antiderivative of a function. Now, we do have to talk about notation though, because when we were doing derivatives, we saw different notations like f prime, we had dy over dx, we had y prime. Okay, all of those were kind of referencing a derivative. For antiderivatives, we have this notation, where this kind of long curly s is called an integral. Okay, an integral symbol. The function on the inside, or written after the integral, is called an integrand. And then you always have this dx or dy or dt, whatever the variable might be. Okay, that's called our variable of integration. Basically, when we do take an antiderivative, we have to work backwards from every x term that we have here, or we're going to be using x's as in our antiderivative setup. Okay, so integral, integrand, and variable of integration. So we have these different terminologies or phrases that we have to be familiar with. So let's see if we can practice one. Let's say we have 3x squared, and I want to work backwards from this function. So if I want to work backwards, I'm going to use an integral symbol, a long s, and my variable of integration is dx. Okay, more often than not, the variable in the function is going to match the variable on the end. Sometimes they can be different, and we'll eventually get to when that might happen. But for now, because this is kind of an intro lesson, the variable within the function is going to match the variable on the end. Okay, you always need this dx written on the end. Okay, if you miss it, it's technically an incorrect notation, and I'll mark it wrong on a quiz or test. The AP people will mark it wrong on the exam. Okay, it's just a part of the notation that you have to use. So if we think about this, if I were to work backwards from this function, okay, with respect to x, we would have to add 1 to the power. So if I added 1 to the power of 2, that would be a new power of 3. And I have to divide this coefficient of 3 by the new power. And so 3 divided by 3 would give us 1. So it kind of makes sense that if I were to take the derivative of x to the third, I would get 3x squared. Okay, see how they're related to each other. So I'm working backwards from this function to figure out what I had previously. Now there is a little problem or issue with this integration or this antiderivative. What if I had a minus 4 on the end? If you took the derivative of this, wouldn't you still get 3x squared? Okay, what if it was a plus 4? Notice how you'd still get 3x squared if you took a derivative. So whenever you do find an antiderivative, okay, the x portion will always be correct, but there could be some constant on the end that we are missing or that we might not know. So that's why whenever we do find an antiderivative, we're always going to add a plus c. And this is just representing some constant of integration that we might not know. Okay, we'll eventually talk about how we can figure out what the constant is. We would need a little bit more information. But whenever you find an antiderivative, we need that plus c on the end. All right, so let's go ahead and just take a look at some of these examples to get used to working backwards. I want to work backwards from this function with respect to x. So let's work backwards from each individual term. If I add 1 to the power, I'll get 3, and 3 divided by 3 would give me 1. Looking at the next term, I'm going to add 1 to the power, which would be 2, and then 2 divided by 2 is going to give me 1. For the next term, technically it would be x to the 0 power, so if I add 1 to the power, I'll get x to the first, and 3 divided by 1 would give me 3. So after I work backwards from each individual term, this is what I get as my antiderivative, but there could be some constant on the end that I'm missing. And if you were to take the derivative of this result, you would get 3x squared plus 2x plus 3. So what's nice about these is you should always be able to check your work by taking a derivative and seeing if it matches what you originally started with. So if I clean this up, just because we're not really used to writing the 1's in there, I'll have this as my final antiderivative. All right, let's try the one beneath it. So very similar to how we use the power rule for derivatives, we have to make sure that it's in polynomial form. So that means x to a power, aka no parentheses, fractions, or roots. Okay, so if you have any of those going on, we're going to have to clean it up or rewrite it some way so that we always just have an x to a power, or maybe just a single number like we saw previously. So in this case, I do have some parentheses. I'm going to expand them out, okay, go through a FOIL process. So I'll have 2x squared minus 3x plus 4x would be 1x, and then the last terms would be a minus 6. All right, so I want to work backwards from each term individually and not forget the plus c on the end. So if I add 1 to the power, I'll have x to the third. 2 divided by 3 is 2/3. For the next term, I'll add 1 to the power. 1 divided by 2 would be a half as my new coefficient. For the next one, it's technically x to the 0, okay, like we saw previously with a 3, so this is probably going to be minus 6x, and then there must be, or there could be, some constant on the end that we don't know. So if you took the derivative of this result, you should get the original integrand back. All right, moving on to the next one, I notice a fraction. Okay, I can't have a fraction, I just want x's to powers. So maybe I can divide each term on top individually by the bottom, because there's only one term on the bottom. That would give me x to the square, or x squared plus 2, and then I'll have minus 4 over x. Now that's still a fraction, but I can move the x up and make it a negative power. Okay, that looks better. So now, when I work backwards, I'll add 1 to the power, divide by the new power. Next would be 2x. And if I look at the last term, if I add 1 to the power, that'd be x to the 0. And I technically have to take -4 divided by the new power of 0, but we know that's going to be undefined. So somehow this third term is not working out like it should. So if that's the case, okay, notice how the other ones worked perfectly fine. If that's the case, then this x to the -1st is probably something special. So it probably has a special antiderivative, just like how we had special derivatives earlier this year. So x to the -1st is really 1 over x. And can you think about, with our derivative studies that we've done, what you can take the derivative of that would give you 1 over x as your answer? Okay, if you really took a time to think about it, or maybe you look through the notes with the special derivatives that we had, that would be the natural log of x. So whenever you see x to the -1st, or like 1 over x, that's signifying an antiderivative for a natural log. So this -4 will keep, just like we normally keep coefficients for derivatives, and our antiderivative of x to the -1st is the natural log of x. So I work backwards from each one. Don't forget the plus c. All right, if you took the time to check your work, take the derivative of this and see if it matches your integrand. All right, now for the last one, I see a fraction and a root, so I'm going to rewrite both of those. A square root can be a power of 1/2, and instead of being in the bottom, I'll move it up to the top to make it a negative power. So now that I have x to a power, I can work backwards. I'm going to add 1 to the power, which would be 1/2. And I have to take the coefficient of 2 divided by 1/2. So 2 divided by 1/2 is the same as 2 times 2, which would be 4. Okay, and don't forget the plus c.